In this video, we're going to be discussing the arithmetic of functions and also composition of functions. This should be a relatively not too long section, but I won't say it will be an easy section. Composition is one of the most important things we can do with functions. We're going to be learning how we can add functions to create new functions, subtract functions to create new functions, multiply them together to create new functions, and divide them, with, of course, the caveat that we cannot divide by 0. Then we're going to learn how to put one function inside of the other function in place of the variable. This last operation is called composition of functions, and you may have learned it earlier as fogging and goffing. It uses an open circle notation, which is different from the symbols we've seen before. Let me share my screen and we'll go ahead and get started. Let's take a look now at problem number 1. In problem number 1, we're dealing with the arithmetic of functions. That is, how to take two existing functions, in this case, x squared plus 8x, and the function 7 minus x squared, and create new functions out of it. Now, this is actually a pretty powerful idea. You're taking two functions that you know because they're functions that they pass that vertical line test. And then you're doing operations on them based on arithmetic that create what is guaranteed to be another function. In fact, you may not have any idea what it looks like, but because the two component functions are functions, the resulting function will be a function as well and pass the vertical line test. Let's take a look at how we proceed and what the domain of each will be. When we're looking at this, we want to first write down the functions that we have. Remember, this is to protect you in case you make a mistake and accidentally think of the wrong function. That way I know what you're starting with. We have two functions, f of x, which is x squared plus 8x, and a second function, 7 minus x squared. These are both parabolas, which of course graph like this, and they're quadratic equations. If you look over here on the left, you'll see that we want to add them, subtract them, multiply them, and divide them. The only one that can cause us a little bit of trouble is division. We cannot divide by 0, so we'll have to be sure to check the domain of the denominator function and make sure to eliminate any x values that would cause the denominator to be 0. When adding the functions, we have to look and see what the domain of each function is, and then we take the combined function and we consider the domain to be whatever they had in common. So if the function of f is all reals, and it is, and the function of g is all reals, and it is, then the domain of the combined function, f plus g, will also be all reals. Again, how do I know that it's all reals? We're looking for things that should not happen on a real number line. Basically, that's division by 0 or a negative under an even radical. Since neither one of these functions have an even radical or a denominator with a variable in it, we know that there are no values that are eliminated from the domain. So the domain is the default domain. We can write the domain with the letter D, and then we can use the double bar R, or we can use interval notation to indicate what the domain of the function is. Now remember, the domain is the set of all x values that get used. Now let's take a look at what we do when we add the two functions together. What do you think the rules should be? You're right. I need to sneeze. It's a weird kind of day. It's May and it is pouring snow outside. And yesterday it was 80 degrees. Gotta love Colorado weather. When we add two functions together, we simply do what it says. We take the two functions and we add them together. Then we can combine our like terms, of which we have two. We have x squared here and negative x squared here. Those will cancel each other out so that f plus g of x becomes 8x plus 7. This is a line. In other words, we added these two quadratic equations, which were parabolas, and we ended up with a line. What's the domain of the new function? Well, the domain of the original two functions was all reals, and when we're adding, we get whatever they have in common. And that means the domain of the new function is also all reals. Let's put our answers in and see how we did. Oops, I've got a backwards parentheses. I'll have to fix that one. Now it looks right. If I check this, let's see if we got green checks for the parts I filled in. The parts I filled in are correct. Let's take a look at the other pieces now. The second part is wanting me to subtract the two functions. In addition, the order doesn't matter because addition is commutative. Commute means drive from one place to another and then back again. And commuting means the same thing, one to the other and then back. In other words, you can switch the order. In subtraction, you cannot switch the order matters. They want f minus g, not g minus f, which would probably be a different function. Let's do this one in a different color just to provide a little contrast. The notation is to put the directions in the parentheses where the functions are. So we have f minus g, and then the x means use x as the variable. It does not mean to multiply by x. There is no x there. There's no multiplication. This means take the function f, subtract the function g, use the variable x in place of the variable. F, of course, was x squared plus 8x. G was 7 minus x squared. To subtract all of g, because it is two terms, I need parentheses around g. Then the negative is going to distribute over both the terms on the inside of the parentheses. This leads to x squared plus 8x minus 7 minus x squared. Oh, plus x squared. Don't forget the double negative. In this case, I again have two like terms, x squared and x squared, but this time they do not cancel. Instead, they double to give me 2x squared. Then I have plus 8x minus 7. This time when I combine two functions, I got another function, as I'm guaranteed to do when I add, subtract, multiply, and divide. But I got another quadratic equation, another parabola. What's the domain of the new function? Again, when we add, subtract, and multiply, it's whatever they have in common, and that becomes the domain of the new function. In this case, both functions had an original domain of all reals, so subtracting them should give us, again, the domain of all reals. Let's enter this in and see how we did on this part. Our function is 2x squared plus 8x minus 7. And our domain is the same as what we had previously, negative infinity to infinity, which I'll copy and paste below. Now let's check and see how we did. 2 more green checks, so we know we're on track. Let's take a look at the third option, which is multiplication. Again, when you multiply two functions together, you're guaranteed to get a function. You're guaranteed that whatever you get passes the vertical line test. What is the domain of the new function? It's whatever the two original functions had in common. That becomes the domain of the combined function. Now let's go ahead and write that one down. And again, we'll contrast the color to keep the parts separate. This time we have f divided by, oops, looking at the wrong one. We have f times g. Multiplication is also commutative. That means that we could have written f times g or g times f. It would be the same, just as f plus g and g plus f are the same. It won't be the same for division, and it's not the same for subtraction. Remember that the x here means use x for the variable. It does not mean multiply by an x. There is no x to be multiplied on that side. There's no multiplication other than the two functions being multiplied together. In order to multiply them together, we write each function inside parentheses, and then we apply the distributive property, or as we like to call it in the United States, the FOIL process. That first terms, x squared times the 7 gives me a 7x squared. The outside terms, x squared times negative x squared gives me a negative x to the 4th. The inside terms, 8x and 7, give me plus 56x. And the last term, 8x times negative x squared, gives me a negative 8x to the 3rd. The last thing that I would do was I would write it in descending order by the power of the variable. It's not necessary, and web work won't care, but that is the typical way we do it in mathematics. So I would start with negative x to the 4th, being sure not to lose the negative, then negative 8x cubed as the next degree down. And then I would have the squared term plus 7x squared, finally followed by plus 56x. This is a 4th degree polynomial, which we'll study in more detail later this semester. This is a new function we created out of two old ones. What would the domain of this function be? Again, we're looking to see what it has in common. F and G both had original domains of all reals. So the domain of the multiplication is going to be also all reals. Let's enter this one in and then check our answer. Again, we get the green checks because we followed the process correctly. The last one is the one that is a little bit trickier in combining functions to make new functions out of old ones. This is the division one. When we divide, we have to remember that there is one cardinal rule in mathematics that we cannot violate. Thou shalt not divide by 0. So when we have this last one, we have to be sure that whatever causes the denominator to be 0 is thrown out of the domain. Let's take a look at what f divided by g would give us. Again, we have the directions in the parentheses, and the x afterwards means use x for the variable, not multiply by x. Then we're going to write the f function first in the numerator, x squared plus 8x, and then the denominator function, 7 minus x squared. Now, the combined function, which is the ratio of these two polynomials, will have a domain that is equal to whatever the two domains had in common minus whatever causes the denominator to be 0. They have in common all reals, negative infinity to infinity, but we cannot allow the denominator to be 0. So we take the denominator, we set it equal to 0, or in this case, not 0, and then we solve it. We can move the x squared term to the other side by adding x squared to both sides of this not equals equation. And this gives us 7 should not be equal to x squared. Then we can apply the square root property since x is in one location by itself and squared, and we can take the square root of both sides. The side without the variable gets a plus or minus, and the other side does not. This tells us that plus or minus the square root of 7 needs to be thrown out of the domain because it would cause the denominator to be 0. So what we're starting with is all the real numbers, and we have to take out these two numbers. On the number line, if you visualize what's happening, we have 0 for a reference point, negative square root of 7 here, and square root of 7 here. We want to include all the numbers except those two. So we have empty circles at those two and bars everywhere else. How can we write this in interval notation? Start at the far left and work your way to the right. The far left is negative infinity. Then it stops with a hole at negative square root of 7. Because it's an empty hole, we use round parentheses. Then it picks up again at the same place, negative the square root of 7, and continues until it hits the square root of 7, where it stops again because that number needs to be left out. Then it picks up at the same number again and continues to the far right forever and ever, which is in the direction of positive infinity. It is very long, but this is what the result would be. Let's go ahead and enter this in now to see what we get for our result. In order to enter the combined function into WebWork, we need to be sure to put the numerator in parentheses and the denominator in parentheses. I can't see what I'm typing. And I need to close my parentheses, which I almost forgot. Down here, I need to start at negative infinity and go to negative the square root of 7. Remember to close the parentheses for that portion. Remember that it is not the parentheses that closes the square root. You need another one to close that interval. Then we use the uppercase U, and then we can start again with negative the square root of 7. Oops, I accidentally typed in equals instead of my thing. Hang on while I stand up and try to see these letters a little better. It's such a pain. Never, ever, ever get what I have, which is a white keyboard. That should be a negative. So I have negative the square root of 7. Comma, square root of 7. Close that, union, another square root of 7. To infinity. If I haven't messed in parentheses up there, it'll be a miracle. Let's check and see how I did. Oops, it looks like I've got something messed up, but we'll see. Let's check answers. I did mess something up. I'm missing a U. Let's see what I'm missing down here. I have negative infinity to the square root and then U. I have an extra inequality there, which is not needed. Let's check it again and see if that fixes the problem. Nope, I still have an extra one. Let's see what's going on. Negative infinity, negative square root of 7, open, then close the interval, union. Negative square root of 7, then I should have a comma. Square root, open 7, close, union, open square root, go to 7, comma, infinity, close. I've got one too many closes. Now let's check it. All green. Gotta love it. Working with web work can be a challenge, but if you keep at it, I think you will find that you can learn eventually how to do it. It would be easier if I had this a larger screen so I could see more of it at one time. The next problem is essentially the same as the previous problem, but because the functions are a little bit different with the square root, we're going to go ahead and take a look at this one as well. In problem number 2, our two functions are f of x equal to x squared and g of x equal the square root of x minus 7, the quantity. Still snowing and starting to gather on the roof. It's crazy. Now we have f plus g of x. What's the domain that we're starting with f? There are no square roots and there is no denominator. So the default domain for f is all reals, negative infinity to infinity. What's the domain for g? What are we starting with? In this case, g will only accept things because of the square root that are not negative under the radical. Remember, we take out what's under the radical and we say that must be greater than or equal to 0, which basically means not negative. Then we can add the 7 to both sides, which tells us that x is greater than or equal to 7. Putting this onto the number line to see what it looks like, we have a closed solid ball at 7, and the variable is on the wide end, so we go to the right. That means our domain for the g function has a square bracket at 7 and then positive infinity further to the right. Remember to make your interval notation follow the number line picture in order left to right. What these two have in common is not all reals. This won't accept all reals. Instead, this only accepts from positive 7 and above. That means what they have in common is positive 7 and above. Let's take a look now at f plus g of x. Again, the of does not mean multiply. This just means use x as the variable, as opposed to t or p or q. In this case, when we add the two together, we end up with 2x squared plus the square root of x minus 7. What they have in common for the domain is going to be from closed 7 to positive infinity. We'll type that in now, but we'll check it all at once. That looks right. Now let's look at f minus g. When we do f minus g, remember that the order does matter because it's subtraction. In this case, it's f first, not g first. And again, they want us to use x. If they wanted us to use a different variable instead of x, they would notate that here by putting a different variable in the parentheses. In our case, they did want x, so we leave it at x. This is going to give us the f function, 2x squared, minus the g function, which is the square root of x minus 7. It might be tempting to want to distribute the negative, but the square root blocks that. The negative stays on the outside of the square root. It's essentially the same as what we had with the addition, but with a different sign in the middle. What would the domain be? Again, the domain will be what they have in common, which is 7 to infinity. Now let's look at the third one, which is f times g. When we do f times g, we need to remember that the order will not matter because multiplication, like addition, is commutative. In this case, we have 2x squared being multiplied by the square root of x minus 7. There's really no way to combine the two because the first is not under a radical and the second is. All we can do is write them side by side, and that's good enough. What will the domain be? Same domain, what they have in common. Remember, G will not allow anything that is below 7 because when it gets below 7, it causes the radicand, the part under the radical, to be negative. Let's enter this information now. This time, instead of having plus, we need multiplication, which we can use with the asterisk symbol, which is above the 8 on the keyboard. That should interpret this correctly. The last one we have to look at is the division. When we do division, the order does matter as far as which one's in the numerator and which one's in the denominator. Again, the x means use x for the variable. It does not mean multiply by x. In this case, we're going to write 2x squared divided by the square root of x minus 7. Now, we have to do the same thing that we've done before. Look at what they have in common, which is close 7 to infinity, but eliminate anything that would cause the denominator to be 0. Well, what would cause the square root to be 0? Only if the radicand, what's under the radical, becomes 0, which means that x minus 7 cannot equal to 0, which means that x cannot equal 7. This time our domain will not be close 7 to infinity because we cannot allow 7 to occur. We'll have to throw 7 out by making the parentheses at the 7 round. That creates a hole at the 7 and will not include it in the domain. This time we use the division bar to indicate division. It should interpret that correctly in WebWork, but we'll have to see what it does. In the denominator, we know that what we want to have is a round parentheses instead of a square one. So we'll move to the front and delete the square one and insert a round one instead. Now let's go ahead and take a look. I hope we have all green. Yes. Now we're moving on to different types of problems or a different method of creating a new function out of old functions. This is called composition. This is one of the most important ways that we create new functions out of old ones, and it gets used an awful lot. It is one of the primary methods we use in calculus and other courses. So if that's your future pathway, you'll want to pay particular attention to composition. The symbol that we use to indicate composition is not a dot for multiplication, but an empty circle of a larger size, like the one you see here. Sometimes teachers in the past have called this fogging and goffing because it looks like it spells out F-O-G and G-O-F. This is actually composition, and it can be written in multiple ways, which I'm going to show you all of the ways right now. When you're doing composition, You're putting one function inside of another function. In other words, you're going to substitute one function in place of the variable in another function. It is possible to compose a function with itself. Now, what are the various ways that we use to show this? In this problem, number 3, they're using the circle notation, which looks like G circle F. G circle F is usually put in parentheses, and then an X follows it to indicate that they want you to use X for the variable, not multiply by X. Again, when you're doing notation, the notation never means multiply by X when the X is in parentheses. What it means instead is to use that for the variable. This means that we're going to compose G with F. We'll say G of F of X. But we don't mean multiply. We mean put F inside G in place of the variable. In this case, we know which one goes in which one because of the order in which they're written. The one that is written first, in this case, the G, is called the outside function. And the one that is written second is called the inside function. We put the inside function inside of the outside function. Now, there's another way that we can write this as well, and this is with nested parentheses, G of F of X. You'll see both of these methods used extensively throughout algebra and in future courses. When you look at this one, I like to make the sets of parentheses different sizes so it's easier to tell. In this format, it's easier to see that F of X is inside G because the parentheses that hold the F of X are actually completely contained inside of the G. This is G of F of X. We can also do F of G of X, but that would probably give us a different function. It's not normal for them to turn out to be the same. We will discover, however, that when they are the same, it means something about the two functions involved, that they're related to one another. In fact, they're inverses of one another, meaning that they undo the operations that each one does. Now let's take a look at the actual operation of composition. Let's start problem number 3. In problem number 3, we have one function, f of x, as negative 2x squared plus 8, and another function, g, as 5x plus 9. The first thing it asks us to find is f of g of x. That means compose f with g, use x for the variable, or we could write f of g of x. Notice that the g is completely contained inside of the f, meaning g is the inside function, f is the outside. The one written first is outside, the one written second is inside. How do we do this? Well, this is basically substitution again. It's exactly what we've had before. This notation here makes it more clear. Write the function called f, but leave empty parentheses in place of the variable. Here's f, negative 2x squared plus 8. So we write negative 2, open a hole, squared, plus 8. What do you suppose we're going to put inside the hole? Yes, of course. We're going to put all of g of x inside the hole because that's what the notation tells us to do. So the next thing we write is negative 2, and then we put the entire g function, g at 5x plus 9, into that hole. Finally, we can simplify it. Now, whether to simplify or not depends on your professor and what level of course you're taking. We'll go ahead and multiply it out and combine like terms. In this case, if we multiply it out, we need to write the 5x plus 9 two times in order to apply the distributive property or the FOIL process. This is going to give us a 5x times a 5x, or 25x squared. On the outside, 5x times 9 is 45x. We get another 45x for the middle, and that gives us a combination of 90x for the inside. 9 times 9 gives us a plus 81. We can't drop the parentheses yet because then this product needs to be multiplied by the -2. So we distribute the -2 over the parentheses by multiplying it by each of the terms on the inside of the parentheses. The plus 8 just tags along. This gives us -50x squared plus 180x minus 162 plus 8. Finally, we combine the two like terms, which are the two constant terms, -162 plus 8. Hopefully, I'm not making any arithmetic errors. This would give me -154. That would be f of g of x. And what is it? Well, it's a quadratic equation. So it's a parabola. And in this case, it opens down because the leading coefficient is -50 and it's negative. Now, when we're looking at this, if we want to know what the domain of it is, we think about the domain of the inside function g. We start with that. And then we say, what values does it put out? Well, it will put out all reals. Will f accept all reals? Yes, it will. So the domain is the domain of g that are allowed gives y values that are allowed in f. Since they're all allowed, then we have the domain of g as the domain of the composition, which is all reals. Now let's look at g composed of f of x, or as some call it, g circle f, or Goffing. When we look at this function, this is the same as writing g on the outside and f of x on the inside. Notice how much of a difference I make in the two sizes of the parentheses. That helps to keep straight which is inside and which is outside. Now what we want to do is we want to apply this in the order that it's written. G is on the outside, so we write the g function and we leave an empty set of parentheses to substitute in the inside function. Then we have the plus 9. This is for 5x plus 9. We replace the empty set of parentheses with f of x, which is a -2x squared plus 8, as you can still see over here on the problem statement. Once we have it written like this, we can go ahead and multiply this out. The 5 distributes over both terms inside parentheses and gives us -10x squared plus 40, and the plus 9 tags along. Then we have two like terms of 40 and 9, so we combine them to get -10x squared plus 49. Let's go ahead and enter that in for our solution. What about this last one? It says f composed with g of -3. Well, we've already done f composed with g. That's the work that we did here in the black type. We got this as our final result for f composed with g. Let's copy this and make a paste of it down here. That's the same thing as f circle g. If we're then asked to find f circle g or f composed with g of -3, this means the same thing as f on the outside, then g, then -3. Now there are two actual ways to complete this, and I'll show you both. The first one is to take the f of g function, since we already have it, and replace the variable with -3. That is, after all, what the notation means. That means opening up a hole where the variable would be and replacing the variable with -3. Now we substitute the -3 in the empty set of parentheses. Remember that powers have to be done before multiplication. So this leads to -50 times a +9 plus 180 times -3 minus 154. The 5 times 9 will give us 45, followed by another 0. So we get -450. 180 times -3 is like 3 times 18 with a 0 at the end. 3 times 18 is 54. So this gives us a -540. For the next term, we have -154. Now we combine all of these together. Since they're all negative, they'll add together and keep the negative. 0 plus 0 plus 4 is 4. 5 plus 4 plus 5 is 14, carry the 1. 1 and 4 is 5, and 5 is 10, and 1 is 11. I'm getting -1,144. Let's check our answers. Uh-oh, I've made a mistake somewhere. Let's go back and see where I made the mistake. The mistake is almost certainly with the first one, because that would have affected the second one. Let's go back and see if we can find where I made the mistake. Returning to the part where we solve for f composed with g, I have -2 times something squared plus 8. That matches the function that I have here. Then I replace the inside with the other function, 5x plus 9, which matches. Boiling it out, I would get 25x squared plus 90x plus 81. Then I distribute the -2, and there's the mistake. Do you see what I did? I multiplied -2 by 90x, and I got a positive. It should be a negative. Let's fix that now. This should be -180x. Let's correct that and then check our answer to make sure that it's correct before we correct it in the third part. That's correct. Moving on to the third part then, we come down here and we make the change here as well. That should be a -180, which will change the middle term from -540 to +540. To work this out, I would combine the 540 minus 450 first, and that would give me 90. Then I would take 90 minus 154, and that would give me, well, I'm trying to think, but -64. You guys check at home. Let's try it and see how we do this time. All perfect. Whenever you make a mistake, it is usually a negative sign. So those are good places to look for it when you do the distributive property. Even when you draw the arrows, you can make mistakes. Let's take a look now at the next problem, number 4. In this problem, we're simply supposed to do f composed with g and g composed with f. Let's go ahead and work that one out now. F is the function, the square root of x minus 2, and g is the function, x squared plus 6. F composed with g, use x, is the same as f of g of x, which means write f, open up empty parentheses where the variable is, and substitute the other function inside. In this case, there's nothing more we can do, but just leave the answer like this. When we look at the second part, we're to do g composed with f, which is in the second order. This means g is on the outside and f of x is on the inside. How do we evaluate that? This means instead that what we're going to do is we're going to take g and write it with empty parentheses instead of the variable, and then we're going to substitute f in place of the parentheses. We could multiply this out, but we can also check and see if WebWork will take it in this form. Let's find out. The first one is the square root of the quantity x squared plus 6, and that closes the square root. Then we have a minus 2. We'll have to check the preview and make sure that it looks the way we have it written here. For the second one, we're going to enclose it in parentheses that are being squared. You might want to go ahead and write the parentheses and do the square first, and then add the 6. Then you can come back and add the inside to the parentheses, which would be square root of x, open parentheses, close parentheses for the square root, then minus 2. Oops, my minus became an equals. Now let's check and see if we've done this correctly, or rather if we've typed it incorrect. And it looks correct. These previews do match what we have over here. So we know we've done it correctly and entered what we intended to enter, and that is the correct answer. In problem number 5, we have fractions involved. Fractions are always difficult for everyone. So let's take a look at the fractions. We have f of x, which is equal to 1 over x minus 4, and g of x, which is equal to 5 over x plus 4. When we practice this, we have f composed with g, use x, which is the same as f of g of x, which means we write the f function, open empty parentheses in place of the variable, and then we substitute the other function inside. Now we could leave it like this, or we could try to get rid of this complex fraction. To get rid of the complex fraction, the only little denominator we have is x. So I could multiply this by x over x. When I do that though, I have to distribute the x over both sets. That would be over the function 5x plus 4 and the minus 4. I can also drop these parentheses now, and that means that I would be distributing over each term. However, before I distribute, I think what I should do is clean it up. Because I have a 4 minus 4, that's going to give me a 0. Always keep the primary division bar longer than the small ones in the complex part. Now, when we look at this, we can think of this as 1 over 1 over 5 over x. I'll teach you a trick to doing these. The top of the top and the bottom of the bottom belong on the top. When they're the same, top, top, bottom, bottom, they go on top. When you have one of each, the bottom of the top or the top of the bottom, they go in the bottom. In other words, if you have A over B divided by C over D, this turns out to be A times D, top of the top, bottom of the bottom, divided by b times c, bottom of the top, top of the bottom. In other words, the bottom of the bottom is the top. That means the x will swing around to the numerator, and this will become x divided by 5. Let's enter this now. We can check our answer to make sure that we've done it correctly, and we get the green check. Now let's look at G circle f of x. Again, of x means use x for the variable, not multiplication. This is G of f of x. This means write the G function, which is 5 over, well, something, plus 4. Then replace the something with the other function, 5 over 1 over x minus 4 plus 4. Notice I made the smaller fractions division bar shorter than the major division bar. Remember what we said last time, the denominator of the denominator belongs in the numerator. This swings to the numerator, and we end up with 5 times x minus 4 plus 4. You could enter that directly, or you can multiply it out, and this will give us 5x minus 20 plus 4, or 5x minus 16. In the next problem, we're actually decomposing a composition. What does that mean, to decompose a composition? When we're decomposing a composition, we're looking at this as if the composed function, which is h of x, which is some f of g of x, is x minus 2 to the 4th. In other words, this has already been composed with two functions called f and g, and what they ended up with was x minus 2 to the 4th. If g of x is equal to x minus 2, what is f? Well, it can be a little more difficult to figure this out because you're having to remember that the inside function replaced the variable x. So f of x would have had a variable in place of this x minus 2. In other words, f of x would have been equal to x to the 4th. Then you would have opened an empty set of parentheses in place of the variable x and dumped inside x minus 2. So f of x is x to the 4th. Let's try another one. In problem number 7, we have that the composed function h of x, which is f composed with g, again meaning f on the outside, g on the inside, turned out to be 4 divided by x minus 5, the quantity cubed. If we know that g of x, the inside function, is equal to x minus 5, what is f? Again, remember that f would have had the variable x in it, and we would have replaced it with an empty set of parentheses, which we would have opened up and then replaced with x minus 5. If we replace the x minus 5 moving backwards with x, we get 4 over x cubed. Let's enter that now. The next problem is very similar, so I'm going to leave it to you to figure this one out on your own at home. Problem number 9 is a little bit different. In problem number 9, we're asked to look at a graph and to figure out what a composed function is at a particular value. Now, one of the things that I did not show you earlier that I promised I would was how to do this in a different fashion. Let's see if we can find that problem. Here it is, f composed with g of -3, where we have f of g equal to that function. Let's copy this problem and paste it below, and I'll show you a different method of finding the -64 answer. Again, when we're looking at this problem, one of the things that we can do is we can replace the -3 into f composed with g. However, this also says that I could find g of -3 and get a number and substitute that number inside of f. Let's go back to this problem and see if we can recall what those functions turned out to be. This was problem number 3 originally. When we're looking at the original problems then, f of g of -3, one option that we have is also to compute g of -3. Again, we would write g opening empty parentheses for the variable, and we would substitute the -3 in its place. That would give us -15 plus 9, which would give us a -6. Then we would take the -6 and replace g of -3 with -6 since they're equal to each other. This means that this would turn out to be f of -6. And we would take the -6 and plug it into the f function. This would be -2 times something squared plus 8. And when we substitute the -6 in place of the empty parentheses, we would have to square the -6 first. -6 squared is 36, and that gives us -2 times 36, then plus 8. Multiplication before addition, so we get -72 plus 8, which leads us to the same result of -64. The second method is more important when looking at a graph. That's what we're going to use here in problem number 9. In problem number 9, what we're looking at is evaluating this particular graph and the value of g of f of 4. Again, that doesn't mean multiply it by 4. That means you have g on the outside. And what you're doing is you're putting f of 4 in place of it. Let's take a look at the graph of f. The graph of f is here on the left. I'm going to click on it and make it larger. When I look at the graph of f, if I can get it to move, which it's not wanting to move, fine, we'll have to leave it where it is. Unless I can get it to, there it goes. When I'm looking at the graph of f, this says f of 4. Well, what is f of 4? When x is 4, what's the y value? Come across to x equal 4, then move straight up in a vertical line till you hit the graph. The y value coming across is 3. So this means that f of 4 is 3. So I'm looking for g of 3. How do I find g of 3? Well, now I go to the graph that is g, which is the one on the right, and I shouldn't have clicked off the other one. Let's put it back up. And now, if I can get this to move eventually. When I look at this graph, which is the graph of g of x, I know I want to go to where x is 3 and find the y value. Remember, notation replaces the y variable. So this means go to 3 for x and find the y value, which would be 4. So this turns out to be 4. What about g of 2? That's kind of confusing. It's using the same function twice. But what it means is to use g both times. This means we have g on the outside and g on the inside. First, we're going to use g of 2. Go to the graph called g, which is here. Come across to where x is 2 and find the y value, which is also 2. This means g of 2 is 2. So now I'm trying to find g of 2. Come back to the graph and again come to 2 and find the y value, which is still 2. This gives me 2 for the final result. So my answers here are 4 and 2. The next problem is very similar to the previous problem, so I leave it to you to practice this at home. Problem number 11 is also similar, but instead of using a graph, we're using a table. Let's take a look at how to apply what we've learned to the table form. In the table form, we have x here, which is the x coordinate for both the f function and the g function. They're listed in the same table, which is a little unusual. Why do you suppose they do that? Well, it's not to help the students, it's to save space. But it means that this x belongs to these y's under f, and this x belongs to these g's or these y's under g. We want to find f composed with g of 4. This means we have f on the outside and g of 4 on the inside. We start with the inside function again. We go to the one called g, and we let x be 4. We find the 4 in the x row, and then we move down to the g row, and we find the y value when x is 4. That gives us 9. Now we're to evaluate f of 9. We go to the x row where x is 9, and then we move to the f row to find the y value when x is 9 in the function f, and that's a 2. The next problem is similar, so again, I'll leave it to you to work on that one at home. The next problem is more fogging and gothing. Let's work it both ways so that we can see how to do it. In problem number 13, we have two functions again. We have f of x, which is equal to 3x plus 4, and we have g of x, which is equal to 7 plus x squared. They want us to evaluate f composed with g of 3, which is the same as f on the outside and g of 3 on the inside. We have two choices. First, we could find the composed function f of g of x. When we do that, we write the f function, leaving an empty hole for the variable, and we substitute the other function in place of that hole. Then we distribute the 3 over each of the terms inside to get 21 plus 3x squared plus 4. The 21 and the 4 combine to give us 25. So we have 3x squared plus 25. Then to find f of g of 3, we simply plug in 3 into this function, this new composed function. Three squared is 9, and 9 times 3 is 27. We get 27 plus 25, which would give us 52. The other possibility is to do what the directions say and first evaluate g of 3. G of 3 would replace the variable x with 3. So g would be 7 plus something squared And when we substitute the 3, we get 7 plus 3 squared. This becomes 7 plus 9, which is 16. Then we substitute that inside of the f function in place of the variable. The f function is 3x plus 4. Three times 16 gives us 48, and 48 plus 4 again gives us 52. We get the same answer either way. Which method you prefer is really a personal matter. It depends on which one you're better at and which one you're less likely to make mistakes on. Choose the method that works the best for you. I'll take either one. Problem number 14 is essentially the same as the ones we've done previously. So I'm not going to work this one for you. I'm going to leave it for you to figure out on your own. This is the end of this particular section. Our next section coming up deals with transformations of graphs, and it's a real doozy. So allow a lot of extra time for the next section, 3.5.